Welcome to SolidWorks Live Design. SolidWorks Live Design is a series we run here at SolidWorks that is dedicated to pursue of learning from one another using the medium of live demo and exploration. As we share our favorite software tips and tricks. My name is Gurpreet, and today we are joined by an amazing YouTube creator, Bogdan, who you likely know from the Hacksmith YouTube channel. The Hacksmith team takes ideas from the world of movies, TV games, and comics to create real world prototypes. Their mission is to make the impossible into reality every day. The moment I saw their website and their videos, I was totally bogged down. Even my 11-year-old son, Gurman, he's also very fascinated when he knew that I'm going to share this screen with a Hacksmith team. Bogdan, before we get into the actual content here, over the next 60 seconds or so, can you tell us why we are doing this episode today, including the three key topics of this episode of SolidWorks Live Design?
Absolutely. So, at the end of the day, the goal of our YouTube channel is to inspire our audience, inspire, people that are learning about engineering and learning about cool sci-fi tech to get excited and to learn more about science, technology, engineering, and mathematics, because we feel like those fields could really change the world for a better way. And I think that, the SolidWorks Live Design fits in with that company why perfectly. And allows us to kind of share some of our experience and some of the more of the behind the scenes of how we make our projects real and some of the design philosophies that we use to create some of the cool stuff that you see in our YouTube videos. And through learning some of this experience, maybe give it a try yourself, and be more comfortable getting into the field of 3D design and engineering.
That's awesome, Bogdan. So this means it's going to be a lot of learning from you today for our audience as well as for me personally as well. So let's take a look at the first topic of the day.
Yeah, so there's a couple of topics that I'm going to be covering. One of the first things that I want to talk a little bit about is sheet metal design. In this world with all the 3D printers and stuff like that, I feel like there's so many different ways to manufacture a single part, but I feel really closely with sheet metal design, not only because of the equipment that we have, but also just because of the ability to rapidly iterate and make parts that are extremely simple, but strong and very, very effective, easy to maintain, easy to manufacture. And I kind of want to show some different tips and tricks. Some people may know a lot about sheet metal design. Other people may not have tried it at all. And I want to kind of get people comfortable with this very useful tool and speed up your process and make parts that are easier to work on and stronger and more practical.
Wow. So in fact, Bogdan, sheet metal is one of my favorite topics in SolidWorks, and in past 18 years, 19 years of working with SolidWorks, I have worked with many customers using sheet metal, but every time when I hear someone sharing tips and tricks, I end up learning a lot. So there are a lot of new things, and I believe we are going to have a great, I can say, input insights from your end based on your experience and the model that you have shown on the screen. It's really, really amazing. So over to you, Bogdan. Yeah.
Yeah, so I guess I'll just give a little bit of a background of this model and kind of the project that we're working on, and then jump into some of the more technical details. So as you know, we build things from fiction and make them reality. And one of the super iconic TV series that just came out, and one of the really iconic exoskeletons that we've seen is actually the Fallout Power Armor. And that's what I have in front of me here. And this is a project that we started about a month ago. And the first episode of this will be coming out on our channel next week. So everybody who's watching this live right now, this is actually the first, you are the first group of people to see this model and see some of the design and some of the progress that we've been making on building real life power armor. And when I say real life power armor, I mean it. So the entire suit is going to be obviously pneumatically powered and is going to be able to curl about 300 pounds and squat about 2,000 pounds. All of these design pieces here will actually be 3D printed initially, inlaid with Kevlar, and then electroplated in a nickel cobalt super alloy, which is going to basically make every one of these pieces bulletproof to level 4. So this should be able to stop rifle rounds. The inside of this is going to be water cooled, so your body is going to be fully climate controlled. It should fit a good amount of different body sizes and accommodate for that. There's going to be a full heads-up display helmet with night vision and thermal vision and Geiger counter and stuff like that. Whole thing's going to be self-contained power pack. So power on the backpack with a compressor, batteries, and a hybrid gas generator. And it should work basically just like the movies. So this is a that we're super excited for. And I really can't wait to show off some of the designs that nobody's seen before.
Yeah. So, audience, do you have any questions for the Hacksmith team? Because I am totally amazed to see this exoskeleton and the power armors. Although I have seen such a armor in museums back in India, the war museums, but ancient war museums. But yes, in real life, I've only seen it today. Yes, it is something like from those Hollywood movies. We are just taking it out into the SolidWorks window.
Yeah. So I guess I'll start a little bit about the design, and we'll jump into some of the parts then, if that's good with you.
Yeah.
Okay. So yeah, I guess the first thing that you see here is obviously a lot of the aesthetics. And so a lot of these aesthetics here, a lot of the suit was actually in partnership with a brand called Thanks, who specialize in sharing a lot of things like 3D models. And so we've been working with them, and they've been helping us design a full SolidWorks model of all the aesthetic pieces as well. And for now, these are aesthetic, but as I mentioned, they're actually going to be full level 4 composite armor once we are done with the project. And these are actually fully featured models designed in SolidWorks with all the individual components, so we can actually modify these, not just to be cosplay, but actually to be full real working power armor and actually make you basically superhuman. But underneath all of that is actually the frame.
Bogdan, sorry to interrupt you. What I've heard, is it right? You said it's a fully parametric model done in SolidWorks?
It is a full parametric model done in SolidWorks. That's not something that I worked on personally, but I really want to give a shout out to them because they have done an amazing job, and they're really what's making this project possible by helping us with a lot of that design. And I've been focused on the internals and actually making that model from a cosplay suit to a real working bulletproof superhuman strength power armor.
Wow, superb. So let's get into the details. Yeah.
Sounds good. So at the moment, this is what we have with the frame. This is still very much a work in progress, but we've actually made a lot of progress on the first arms. And this is what you're going to be seeing in the first episode coming out October 23rd. So I'll jump a little bit into the arm section here. And this right here is basically a exoskeleton arm piece, which will allow the user to curl 150 pounds per arm. What we have in the front here is just 2 pneumatic cylinders, and the whole thing is actually done with basically box tube and sheet metal. So we can actually put one of these together from going from a SolidWorks design to a fully completed arm in about 2 days.
Wonderful.
So that kind of gives you an example of why SolidWorks and using sheet metal can be so powerful. Because if this was 3D printed, especially if we're trying to do like metal 3D printing or something, that would significantly add a lot of cost. It would add a lot of complexity, and it would slow the process down a lot. And by making the sheet metal, that allows us to actually fabricate something like this extremely quickly, put it together and modify it and make iterations on it very, very easily. And in fact, it's not just a 3D model. I actually have the full arm right here, and I can talk a little bit about how this works. But the arm itself has got 2 pneumatic cylinders in the front, and the back section actually is a clamshell. So this opens up just like so, and there's 2 pneumatic cylinders on the side there, which allow you to do so. And then you're able to put your arm inside of it. Whole thing closes around you. There's 2 pneumatic latches on the side here, and that will actually keep it closed. And inside of there is actually a pressure cuff. So the same kind you'd find for measuring blood pressure, This is hooked up to the same pneumatic system, which will inflate around your arm, locking your arm in place, making it very comfortable, and acting as padding so that if you do take an impact or the bulletproof arm actually stops a projectile, it's able to absorb that energy rather than putting that energy back into your body.
This is truly incredible, Bogdan, because just few minutes seconds back I was just visualizing that how I'm gonna use it, but now it's in front of me, and it's truly practical, the way you have designed and the way you have put the padding so that the impact will be taken care by the rest of the structure, and or the human who is going to wear it is not going to get any sort of a discomfort.
Exactly. And so the goal is to actually put water cooling in here as well, because as it is right now with all that armor, you're going to be quite warm. And so the entire body will actually be fully climate controlled, just like EVA spacesuits or racing suits. So a lot of very cool stuff that goes into here. But I guess let's talk about how some of these sheet metal parts were designed and how we were able to build this. We put this whole thing together without the fabric interior in about 2 days, but including all the pneumatics and all the plumbing, wiring, and all the sewing done for the internals. This took us about a week to put together. So we have a very fast iterative process, and that's allowed through, planning ahead for the design and, manufacturing, in very simple ways, such as sheet metal.
Yeah. So this means you are taking art to part and also in a manufacturable way. So
exactly.
It's like the design for manufacturing thinking also is truly in play, because when we think of getting something creative, many a times that manufacturability goes for maybe a toss, but here you have consider it very judicially. Yeah.
And so that's what this would look like on you.
Oh,
that allow you to curl. And there's actually a ball joint that goes up here that gives you full shoulder flexibility and takes the weight of the arm or whatever you're lifting off of your back and into the legs.
Super. That's incredible.
Okay, so let's talk a little bit about SolidWorks and some of the design principles that I went through with this. And one of the first parts that I want to start off with is these ribs right here. And these ribs, they're at the end of the day, they're a pretty simple part. So those who have used a lot of SolidWorks sheet metal probably wouldn't have much of an issue with this. But what I've noticed a lot with people that have used SolidWorks sheet metal is they either go from a solid body to sheet metal, or they go from a flat pack to, okay, let's do all the bends and make sure that the final assembly fits into my part, or the final part fits into my assembly. But I think I kind of want to highlight a little bit here about the flexibility of SolidWorks sheet metal and how you can really jump back and forth quite a bit while still having something that you can unfold, laser cut, and create a really simple part really quickly. I guess before I even get into that, why sheet metal, right? Basically, 3D printing is great, but 3D printing in most cases is limited to plastic. Metal 3D printing, very expensive, pretty slow, hard to iterate on. With sheet metal, not only can we do things like wood or acrylic, but we have a fiber laser cutter, which can do up to, I think, 18 millimeter steel plate. So we can do about 3/4 inch thick steel plate and make some very strong parts very, very quickly. And this rib on our laser cutter would take about 15 to 20 seconds to cut out. Whereas even if we were to 3D print this on, some of the new printers like Bamboo's, this would still be about an hour-long print. And this is out of aluminum, right? So allowing us to save weight and make parts very, very quickly. And then if we need to iterate on that or change something, we can do that in no time. So
incredible. Yep.
I'll jump into a little bit of a new part here and kind of show how I can design something like this quite quickly. So the first thing I'm going to do is just start with a simple sketch. And in this case, we'll start with a flat pack and then turn it into, the final part. So what I might do, for example, is draw a couple of concentric circles. Maybe make this one like 6 inches in diameter. That's roughly the diameter of the hand. Give these two a 1 inch. Probably work in imperial system. There we go. And then I'll draw a nice little triangle here. Make these two equal. And and then throw an angle in between here. Let's just say that this rib is going to be 90 degrees end to end. Make this horizontal. So now it's fully defined. And one of the cool things that we can actually do, one of the features that SOLIDWORKS has recently added that I really like is the ability to trim to construction geometry. So if you just click this little checkbox here, we can now basically trim a lot of these parts off and just keep the parts that we're going to be using while keeping all the relations and keeping all of the dimensions and everything without removing any of the actual lines.
Amazing. I believe this is a very useful enhancement when we are creating some sort of a complex sketches. Yeah.
Exactly. And that way, if you ever do need to change things around or add extra features, you've already got the construction lines there for it.
True. And it end up in creating a neat, clean sketch to start with. Yeah.
Exactly. And so now I can offset entities and say I do a 1/4 inch offset. I can do that bidirectional with arcs as end caps. I've got this part here. I'm going to convert the center into a construction line as well now. And I'm going to extrude that as, let's say, 1/8 of an inch piece of sheet metal.
Yeah.
Right. So we start with something like that. And now we can very easily go ahead and turn that flat piece into our 1/8 inch piece of sheet metal. We can specify, for example, our bend radius here. And now we can work on this part as if it is sheet metal. And what's great about that is we can add a lot of different features here. Things like, adding jogs or, sketched bends, corners, that kind of stuff. So I'm actually going to show that to you. We'll add a quick bend in here. So, and the bend is actually quite simple. We can do a sketch just like we normally would. And let's say we add, a line right here. We want to make this tangent to that bend there.
Yeah.
That'll just be a construction line. We actually want the bend to move a little bit forward so it doesn't interfere with the inside of our tangent line there. So I'm going to make these two parallel, add a bit of a gap there. Let's call that 1/8 of an inch. And now we can go click on that, do a sketch bend, select our face. And now we have a tab here, which we can use for our rivets that are actually going to be holding it to the rest of the section. And
in fact, Bogdan, it's a great tip, especially for people working in sheet metal, where you have taken a construction line and then created a parallel line to define the line of bend, so that the bent material will be you can say taken care, and you get the exact geometry. Yeah.
Exactly.
So,
yeah. And the nice thing with that is you can now go fine tune that without having to change your band angle, or if you're using a different kind of brake or you're using a CNC press or something to do the bends, you can actually adjust the location of the bend directly in here. So you can have it be on the inside, the outside edge, down the center line. Really gives you a lot of flexibility while maintaining the same geometry. And just as easily, we can now go into here, for example. And if we wanted to do bends on both sides, we can make an infinite line down the middle, mirror this across. Oh.
Yeah. Bogdan, we are getting few questions. So since you are creating the sheet metal part, so probably I'll try to take few for you. So from one of our users, they are asking, is it going to be all steel?
Most of the section is actually going to be aluminum. Since not every single joint is going to be powered, we do actually want, to reduce mass. Because if you're swinging this whole arm around, and even if the arm is supported by the weight of the legs, it's still a lot of mass to get accelerating and a lot of mass to slow down, and you don't want it to tip your entire body. So this entire arm weighs about 14 or 15 pounds. It's actually quite light. And it's all made out of aluminum, other than some of the stainless steel on the fittings, but all the ribs, all the box tube is aluminum, and it's all bolted and riveted together. So that's what allows us to join it all together really, really quick. And the rivets are lighter, and they're easy enough to drill out if we need to make modifications. So yeah, and so far what I've shown is pretty standard design practices for sheet metal. But one of the things that I want to show off is you can kind of intermix the same kind of design style you would use with solid body modeling in sheet metal. So we can just as easily go into here, for example, start a sketch on the inside here, convert this edge, add, for example, a screw hole over here. So let's say we have a 1/8 inch rivet over there. I'm going to put a hole through there. And even though that wasn't done as a sheet metal component or design ahead of time, we can still very much, flatten this section, and that'll keep that hole exactly where that should be in the final one. And similarly, there is the ability to add corners, but if we did want to just use, a standard fillet or a standard chamfer on here, we're completely able to mix and match whether or not we're using, let's do that a little smaller, whether or not we're using sheet metal to actually create our parts. And then the great thing about that is, let's say we have this part, we can flatten it, and now we can simply export that as a DXF. We can even go into sheet metal here and export, for example, bend lines or sketches. Then when you hit export, we have our final geometry here that we can simply send to the laser cutter that will be able to manufacture this in probably about 10 to 15 seconds. And
I think it's incredible. So you have started building your sheet metal part, and then probably added a base flange, added few bends, added a hole, and then also used chamfer to basically remove some material here as well. I believe this is something incredible, and the way you have taken the DXF out. We have a few, I can say, audience, I can say, comments, so wherein they have not used SolidWorks sheet metal functionalities, and they feel it's totally incredible. And I think anyone who is working on sheet, I can say, metal fabrication or product design using sheet metal, using these functionalities are going to really add to their overall productivity.
Absolutely. And as you saw, I designed this whole part very, very quickly, and I can make iterations on it after the fact. Even though it's been converted to sheet metal, it's very easy to make changes to it, to re-export it, get it laser cut, get it bent, and have a part within a few minutes. A part that's, metal. And not only metal, I want to bring to the idea that, if you are just working with plastic and you have the access to, a CO2 laser cutter that can do acrylic, we can do things like bends in acrylic as well. So you can laser cut a piece of acrylic, heat it up with a heat gun or a blowtorch, put it over the edge of a desk and bend it down. And now you have the same geometry as if you would, 3D print this entire section. But it's very, very quick. And acrylic, you can also glue together very easily and very strong using acetone, which makes it easy to, join parts together without using super glue or hot glue, making very clean parts. And they can be transparent as well. You can use these as light diffusers. You can use these as... you can engrave these and have different designs in that without adding any extra process time.
I believe it's a great advice for especially makers as well as people into prototyping, a quick prototyping technique that you have just shared.
Yeah. And one other thing that I want to show off is right here, we went from a flat design and added, bends using, the sketch bend feature. But just as easily, we can actually... let's actually just go right back here. Let's say that we have this design here. I'm going to edit this.
Okay.
Just as easily, we can, instead of having, this entire thing designed initially as a flat pattern, we can, let me actually, how do I want to do this? Let's delete this for now.
Yeah.
We can take this entire section and make it a solid body and then convert it to sheet metal from a solid body the other way around.
I believe it's just a matter of, I can say, a choice. Few people like to go with the flat pattern way. Someone likes to go with the creating a solid body and then converting it into a sheet metal, right?
Exactly. I want people to kind of know that, you can kind of go back and forth, and you're not limited by one feature or another, allowing you to basically, have a part that starts out as a solid body with a couple of bends, unfold it, then add a bunch of other bends and shapes,
Yeah.
fold it back together. So as you can see here, if I were to add, this flange here, now this is a full solid body. This is 1.25. This is a full solid body, and these are merged together.
Yeah.
And now I can, take this, convert this entire section into sheet metal. I'll probably have to delete some of these.
Yeah, maybe you can just delete these.
Yeah, I'll just get rid of these.
Yeah.
Then I can convert this into sheet metal, and we can actually collect bend edges right in here. So I can basically select that bend edge, and now we're going from a solid body with multiple extrudes into that same flat pattern we had before.
Yeah.
You can actually mix and match whether or not you work in sheet metal or whether or not you work in solid bodies, making some very complex geometry that you can then unfold, laser cut, and have a really solid part.
So what's going to be your advice, Bogdan, to especially for our users? So which way is better? What I feel, I'm comfortable with both, but what's your advice to especially someone who is new to SolidWorks sheet metal?
I've used both for a couple of different things. If there's a lot of complicated geometry, a lot of complicated bends that all need to line up. For example, we were making a half-scale Cybertruck based on the Tesla Cybertruck design, and that actually just generated the entire body initially with all the chamfers and all the the cuts and all the angles, and then unfolded that into a flat pattern to be able to laser cut and actually make a full stainless steel body that we can ride in. Whereas something like the power armor here, I actually started with a flat pack because I wanted to make sure that when these tabs were flat, they weren't going to interfere with one another. So they could actually, be flat packed without having any kind of overlaying layers. And then be able to, fold those into the geometry that I wanted. So in that case, I went the other way around. But in both cases, there's always design and engineering changes that have to happen throughout the progress. So I like to mix and match both of those. So even if I might have started as a flat body or as a solid body and flat patterned it, I might go back in and add the holes or mounting features for, our windshield or whatever in the flat section. Or vice versa, even if I might have started something like this as a flat body and bended it, I might add things like chamfers or corners or a bottom lip, for example, to make it, tangent to the actual curve of the arm after the fact. And usually that works really well and can, simplify the design quite quick.
Amazing. So I think these tips are going to be pretty beneficial for our audience today. Yeah.
And then kind of starting to move on to the second topic that I want to cover a little bit. It's still going to talk a little bit about sheet metal, but there's another really cool technique that I want to show off, making some more complicated geometry.
Okay.
So I am having an interesting bug, and I've noticed this recently. I think it's just while I'm streaming, where my computer doesn't want to open new parts for some reason. So I'm just gonna go remove this for the time being, and we'll just start a new sketch real quick. So let's say you have a pretty complicated piece of geometry, and in this case, I'll use a spline to create that, and the spline here will actually do the same thing we did before, which is where we offset entities. We'll do bidirectional. Let's do a 1/16 of an inch in each direction for this one. And we'll just do line ends on here.
Okay.
And I'm going to convert this line here into a sketch line. And let's say we're going to extrude this, geometry. And let's say that the plan for this geometry here is to create this as a sheet metal part that we're planning on forming by hand. Let's say this is pretty thin sheet metal. We want to just bend it by hand or use some kind of like French wheel or forge it. We can even add more complicated stuff. Like let's say we go onto the top here, and this might have like mounting holes or some kind of cutouts. Let's do a quick sketch on here. Let's add a hole right there, for example, and say, okay, well, this is, there's a clearance hole that's going through this part. Okay. Well, what we can actually do is there's a really useful tool that allows us to actually flatten this. And it's just called surface flatten. You can find it in the menu there. I know it does exist somewhere in the other menus, but that's usually how I find it. And what this allows us to do is actually convert this complex geometry into a flatpak file. So we can actually select that geometry, it converts it to a mesh, and then flattens it out for us.
Superb. Yeah.
So
any non-planar geometry, if we want to flatten it out, we can do easily with a surface flat.
Exactly. Right? And whether you have surfaces or whether you have lots of extrudes and chamfers and fillets, you can actually just take that entire model, flatten it out, and now you can basically have a blank right here that you're able to laser cut, or even cut out a sheet of paper, tape onto a piece of sheet metal, cut it out with a pair of shears or an angle grinder, if you're doing this by hand, and then be able to now have a really good reference that when you bend it, it can actually match that geometry perfectly, as long as you can get the angles correct.
I think it's a really good manufacturing tip that you have shared with us. So wherein creating the flat pattern and then putting it on a paper, gluing it to the metal, and then shipping it out. I think not only we are able to get the design tips and tricks from you on SolidWorks, but yes, a lot of manufacturing tips as well.
Yeah, so a lot of people that might not be able to make this kind of stuff, they might not have an $80,000 fiber laser cutter that can do steel. Yeah. But if they have an angle grinder and a paper printer, you can take the same DXF, print it out, in 1-to-1 scale, literally tape it onto your piece of metal, angle grind it out, bend it with a pair of pliers and a vise with a hammer, and now you have parts that you can literally create. They can literally create this with no additional machining equipment or tools. You don't even need a 3D printer.
Wow.
Sorry, my camera here is following me.
It's totally practical manufacturing, you can say, tips you are giving, because since you have already worked on what I believe is, I think you have only developed these techniques while working on the sheet metal and other manufacturing, you can say, functions.
So a quick and easy way to create strong metal parts with very inexpensive tools and materials.
True.
Okay, so, and the reason I was showing this is because, if we come back to the power armor, that's basically how we did these sections right here. So these sections right here are basically just sheet metal sections.
Okay.
That we designed using an extrude and a cut from the side and the top. Very simple design mechanics. But now we're able to flatten that surface, laser cut it out, literally bend it around a pipe, and then add the ribs to it, and create this relatively complex geometry with very simple equipment.
It's totally amazing. So the best part is, whatever tips and tricks you are sharing, you have actually used them in this armor design. Yeah,
absolutely, and that's kind of the goal, right? We want to make, as a YouTube channel who's trying to inspire, we want to be able to get people not to shy away from this. We have crazy machines and crazy equipment. We have, I don't think, like 50 or 55 3D printers at this point of every type, from nylon SLS powder printers to, basic FDM to resin printers. We're getting a metal printer soon, hopefully, and, laser cutters and stuff like that. But we don't want to scare people away and say, okay, well, you need all this fancy equipment to be able to make cool stuff. Because, with the right design tips and tricks and with the right design philosophies, you're actually able to do quite a bit with simple, hand tools and simple working in the garage. In fact, our first exoskeleton that actually kickstarted the YouTube channel, the Hacksmith, was built in James's garage with a drill, an angle grinder, and random hardware he got from a hardware store. And he was able to curl, I think, 275 pounds. So pretty close to what this is. Obviously, the level of comfort and the complexity of the design was not the same as this. But the functionality and the ability to do that in a garage at home was still very impressive.
It's truly impressive and truly inspirational, Bogdan. Moving forward, audience, we are also going to touch upon a few tips and tricks on configuration as well as on patterns as well. So yeah,
Absolutely.
over to you, Bogdan. Yeah.
Okay, so in terms of configurations, I want to show off a really cool part of this on how we actually managed to do this. So this right here is a pretty complicated. Sorry, I want to you have the intro there. This right here is a pretty complicated helmet geometry that we wanted to be able to open and close. So when we worked with things and the initial model they gave us, it's a full solid body model. Let me see if I can open that up over here. So this full solid body model here of this helmet doesn't have individual parts and individual components in geometry. So how can we turn something that is a solid body like this into a system that actually has real moving joints where the helmet, for example, can open up? Because in the show, the helmet opens, and as you can see, that is a pretty complicated geometry to cut out and get all the angles correct, and be able to have a single body separated into two and adding features like, you know, pneumatic cylinders on the inside that can actually pivot this helmet open and closed. And for reference, this helmet is going to have basically a pair of AR goggles integrated into it with a thermal camera, a night vision camera, a Geiger counter, a compass, heart rate sensors. Is going to show up your pressure and your battery level of the system, basically floating in front of you. So you'll actually have an overlay, for example, of a thermal image over what you're really seeing with zero latency, zero delay as you're wearing the suit.
I'm actually imagining myself inside a Hollywood movie, maybe Marvel or any superhero movie, and then all these gadgets we are only able to see over there in those series and movies. But like here, I can see practically you are developing all these equipments that can be worn and one can experience as well. Yeah, it's really cool.
Exactly. So yeah, I'll show a little bit about how that was actually done through a couple of configurations, and how that was able to be separated out really quick. And then I'll show if people aren't working with something like this, I'll show a couple more tips and tricks that you can use for general hardware to be able to make more flexible assemblies. So let's actually open up this part here. And as we know, we want to remove this faceplate. And this could be done with some complicated surfacing features and trying to create a, really, unique like surface around all the edges and then using that as a split line. But there's actually a really simple technique that I found. So what I'm going to do here is I'm going to simply do a sketch on the side here. And we're going to go around really roughly for this example here and kind of follow some of the geometry of this helmet here. So we can go through and say, okay, well, let's say we're going to be cutting this section out just like so.
So is it a type of a split line we are creating, right?
Very much so, using a split, exactly. But a split, most of the time, unless you have the complex geometry and you have all the different faces individually, most of the time when you're doing splits, you're doing straight lines. In this case, we got a pretty complicated geometry. And, if I was to do this for the final design, I'll go through and I'd actually convert all these entities and figure out what lines I actually want to separate from. But in this case, I just did a rough sketch one here, and we can see how this will turn out. But now what I'm able to do is do a cut and remove this front section. So we're going to do a cut extrude, remove those from both sections. Now, there is some... As I said, special geometry sometimes requires a little bit of extra work. Let's see where it might be clipping through. Okay, so now we have that helmet, but now we're missing the front face. And we want that front face to have the same geometry to match up to the back face. So what I could actually do here is I could roll this back once, and I'm going to actually copy this individual body. So I'm going to go into here and say copy, move copy bodies. So I'm going to use that tool there. And we're going to select this entire body here. And we're not actually going to move it. We're simply going to just select this entire object here. Give it just a second. We're going to keep all the motion at 0. It'll probably say nothing's been, applied, and that's perfectly fine. We're going to give that a second. So now we have 2 of the same bodies. And the reasoning for this is we're going to, do this cut, but this cut is only going to be done on one body. So if you look here, we have, this one body that has the front face and the other one that doesn't. And now what we can do is we can use our combine feacher.
Combine. Okay.
And this is, a boolean subtraction. This is a feature that's often used for working with meshes and, in other softwares. And it does actually work quite well in SolidWorks, where we can actually select our main body and say, okay, well, the main body is the one that has the face shield. And then we're going to actually subtract the, let's open this up here. We're going to subtract the body from that we just had the face cut off from.
Okay.
So I'm gonna, this one here is going to be our solid body. This one here is going to be our secondary body. And if that's selected correctly in the correct order, let's hope that we should get just the part that we removed earlier, which will be our face shield. Let's just select this one for now. Body one. And there we go. So now we have our face shield, and we also had our health. So now what we can do is we can go into our configurations, add a new configuration, say face, and this will be our just our face section. We can go back to our original configuration and basically suppress all the previous features here. So now we have our full configuration as the whole body. We have a separate configuration as just the face. And similarly, we can add another configuration and call that, the back of the head.
Okay.
And the nice thing about this is it doesn't have to be a single cut. We could have done this in multiple cut extrudes. We could have done lofts. We could have done revolves, a bunch of different stuff. Remove all the material we don't want, and then create that copy. Use combine to remove everything we didn't remove, and then have basically a section of the body that is separated from another one using some very complicated geometry, right? So such as trying to follow this entire contour all the way around.
Bogdan, I believe with my so much of experience working with SolidWorks, I have learned a lot today, especially on the use of this boolean. The combine tool that you have used, I think this is something is a great learning for me personally today, and I believe the same for the audience as well. And just to summarize, so what you have done is with that solid body, you have taken traced out a sketch where the split should happen, and that too, it's not a straight line split. It is going to be I would say a 3D split that eventually has happened, and then you remove the one portion, copied the body, and then use the boolean operation to create another you can say cutout, and then use configuration to manage it, so that once you create the assembly, you are going to add different configurations of the same part, and then you are going to add rest of the features. I think it's totally truly amazing.
Yeah, absolutely. And that, that allows us to create some pretty complicated geometry and work with this complicated geometry without having to use things like surfacing. I believe there's a question about FE analysis on the structure. The arms have been through FE analysis. So these things here, we did run a full stress analysis on them, and they have a factor of safety of like 8 to 1. So more than good enough. The legs, I believe James ran FE analysis on them about 8 years ago. The ones that you see in the body right now, we're going to be modifying them and improving them. But absolutely, all of our parts that are going to be under loading are going to be ran through FE analysis, and make sure that they're not going to harm the user. Because if you're picking up a car, if you've got 2,000 pounds of weight on your legs that are supported by pneumatic cylinders and that fails, you're going to have a really, really bad day. If you're a fan of our channel before, you've seen our Aliens Power Loader. We actually built a 11,000 pound mech, and it was actually at 3D Experience World last year. We brought it over and we actually did a demo that can pick up 3,500 pounds, and all of that was very much designed the same way as I'm showing today, using sheet metal. It was 3/8 inch plate, but it was basically sheet metal at that scale. And all put through FEA analysis, and had some crazy forces up to, I think some of the cylinders there put out 250,000 pounds. And so far it's still one of our most reliable and one of our most successful projects.
That's truly, truly amazing, Bogdan. So there's a lot of learning we have been through, and I believe in the next section also we are going to learn few new things as well. So what do we do? Do we move to the next topic, or we have a few more things to be covered here?
Yeah, I think we can step on to topic number 3 a little bit, which is going to be kind of similar to what we just talked about. So kind of following the same flow and progress. And then if we have a little bit of time, we can jump back to and show some of the patterning techniques as well. Okay. I did cover a good amount of the patterning techniques that I want to share with you today in a previous episode of SolidWorks Live. So if you actually look for the lightsaber, I showed some of the design features that I use for building a real-life working lightsaber, which now has actually been tested and does function. We're waiting on some parts to make it a little more user-friendly, but this right here will create a 14 kilowatt flame that is about 3 feet long at 4,500 degrees Fahrenheit, basically the same as an oxy-fuel flame. So this holds liquid oxygen here, butane in here, and it can cut through steel like butter. So there is a previous SolidWorks Live episode on this here, and that talks a little bit about the patterning as well. So if we don't have time for that today, make sure you check that out and look at some of those tips and tricks there as well.
I remember, Bogdan, I have seen that episode thrice, because there are so many things to learn, and I request the audience to go whenever you are back after this, you can say live, go back, do watch that episode as well, and also subscribe and like the SolidWorks channel as well as the Hacksmith YouTube channel as well. Yeah.
Absolutely. And so yeah, like we talked a little bit about some of the complicated geometry here, but I want to kind of take a step back and go back to something a little more simpler and a little more close to home with some simple geometry, and how some of these same techniques can be used to improve things like fasteners and hardware. So basically, a lot of the suit, as you will be able to see, actually uses things like pneumatic cylinders. And obviously, a lot of this equipment here, we're not building this equipment from scratch. We are purchasing that. And we use McMaster-Carr a lot. And the great thing about McMaster-Carr is they have 3D models of almost all of their hardware. So I can actually pull that up onto my screen right now. And here is, the design page of this pneumatic cylinder that I'm using on the biceps. And what we can do is we can actually go through 3D SolidWorks and actually download this this file here. Open that up here. I already got this downloaded here. Hopefully we can open that file up.
Okay. So, Bogdan, in the meantime, there is a question. What about the legs? What kind of load carrying capacity do they have?
The goal is to be able to squat about 2,000 pounds. So we should be able to basically connect the suit to a trailer hitch and pick up the back of a car using the legs. So about 300 pounds for the arms and about 2,000 pounds for the legs.
Super.
So yeah, here we are in SolidWorks, and we've just downloaded this part. And as I mentioned, McMaster-Carr is amazing in the fact that they have a lot of the dimensions and a lot of that technical drawing already done in SolidWorks. And you can see here's the final part. But unfortunately, this final part has this piston here that is simply just a separate body that is just made transparent. So if you actually look at the configurations, this is just a part, and this cylinder doesn't move. right?
Yeah.
And when we're trying to design something like this arm here, we want to make sure that the cylinder does actually move. So if I make this subassembly flexible here, we should be able to actually pivot this cylinder all the way up. And you can see that that's fully moving there. And this is super useful for doing things like checking clearances. So you can see, you know, as this comes up, we can validate that all of the parts have clearances, and even these ribs here have little cutouts to accommodate for the cylinders in the, you know, in the way. And being able to do that is really, really nice. So how do we convert this, you know, really nice model that we got from SolidWorks or from McMaster Carr into a flexible model? And I'm going to show you a really quick way that I found. And this is not just for pneumatic cylinders. This is also for things like hinges, right? So as you saw on that arm, there's a hinge for the opening and closing. And again, if you were to download that from McMaster Carr, great part, lots of the dimensions, but it's a solid body, right? Or a couple of solid bodies in one assembly or in one part. And if you want to make an assembly that actually has the motion, we need to break those parts up. So here's how I would do it. There is a feature called keep and delete body. And what this allows us to do is basically say, okay, well, let's make a configuration without this rod at all. So I'm going to delete those two parts there. Okay. And now we have no rod. And then I'm going to create a new configuration just called rod. And what I'll do in that configuration is I'll suppress that delete keep body. And hopefully we can hide this one here. Or I guess we just hide body. There we go. And now I can do the exact same thing and say, okay, I want to, you know, keep, instead of deleting the rods, I want to keep the rod.
Yeah, keep the rod. Yeah.
And so now we have two configurations here. One for just the cylinder. We can just suppress this right here. And if I unhide that, so there's just our cylinder, and then here is just our rod. And now we can very simply do an assembly. Yeah. Insert component. We can insert our round body cylinder, and here we can select, okay, well, we're going to just do, you know, just the cylinder. Insert component. Not browse, we've got it open right here. We're going to insert just the rod. We can very simply mate the diameter of these two, or sorry, the circumference of these two. We can log the rotation because, you know, even though it rotates in the real world, this just keeps the mate a little bit simpler. And then we can even do something like an advanced mate to limit our range of motion here. So if we actually go back to that, this part here, we know that, you know, the extended length is 13.51 inches and our stroke is 4 inches. So 13.51 there from the front here to the back here. I can set a mate. We're going to do over here 13.51 inches. And so we know that that's our full extension. And now we can go to our advanced mate over here. Advanced mate. And we can do distance. So we're going to have a distance mate here. We already know our distance right there is 13.51 inches. And then this one here will be 13.51 inches minus 4 inches.
Minus 4 inches.
And there we go. And now we have a assembly of this pneumatic cylinder, which has the rod move just like it would on the real cylinder with our limits. That is going to allow us to test things like clearances and motion.
It's incredible way to create a functional assembly from this solid part. I think many a times we end up in redoing probably models, creating cylinder separately, creating rod separately, and then putting it together. And the way you have shown, I think it is going to really speed up our process of creating a functional assembly from a solid body. I think it's a great takeaway for us today, especially from the we can say assembly perspective.
Absolutely.
And something I really liked about that is every time you use a command, you can say search tool, and it's a very small enhancement that we have seen in SolidWorks so many years back, but it is always going to add value, because I also, it's very hard for me to remember all the commands in which menu to go, or maybe look for the icons. The quickest way is to go to this search command, and then quickly type the name and get the command over here. Yeah.
Yeah, and I think SolidWorks has so many great tools and so many different options to make different parts. One of the biggest things that I really like sharing with this kind of stuff is, there's a lot of tools that you may not know you don't know about. And just being able to like hear about this tool, and then, later down the line, you're designing something, you're like, oh, I want to split these two bodies down this really unique geometry. And you're like, oh, I remember the combine tool. Let me try to search that tool up and give it a try, and that can save you hours of trying to use surfacing, for example.
True. So, truly amazing to see the way you have, I can say, shown this example of the headset, where, because if traditionally we use a surfacing approach, it's definitely going to take us maybe hours or days together to get something totally aligned, and then create the cutout, and then try to match all those complex surfaces. Yeah, so it's really going to be a real time saver for us.
Absolutely. And that's our goal, remove as many boundaries between, a 3D model and a real part. And sometimes, having these quick tips and tricks saves you a lot of time here and makes it easier to come back and make changes later. So, if I wanted that helmet, I wanted to, say, include the lower jaw now. It's very easy for me to go in and change that sketch without having to remove a bunch of old surfaces and add a bunch of new surfaces, saving time in the long run as well.
True. So, Bogdan, thank you so much for sharing all these, I can say, tips and tricks, and especially the 3 key lessons that we have learned today from the SolidWorks live design. So how about if we do checks the chat here, and let's go through few questions, probably at the to end the episode. And before we jump onto that, Bogdan, would you like to give a shout out to anyone for today's content and today's episode? Yeah.
I think there's basically 2 shout outs that I kind of want to mention. The first one is Thangs. We actually have our own Thangs page now, and Thangs is a platform for sharing 3D models. And they have a lot of things for 3D printing, for example, such as our power armor is going to be on Thangs, so that people can actually subscribe to us, support us throughout this project, and get access to the STL models that we're going to be making that will be fully 3D printable, already cut up into multiple different sections, so you can print it on your home printer and create really cool cosplay. For next Halloween, for example, you can 3D print all of these parts, the full suit, and actually wear it, even if you don't have the full exoskeleton, as a really, unique piece of art, basically. And that helps support us to be able to make things like this, but also allows us to give back to you through some of these models, and allows you to, get something really cool out of it.
That's amazing, Bogdan. So do subscribe and like this episode if you have learned anything. It's the most functional way to thank you here on YouTube. So I believe we'll be back with a new episode next month. But before saying adieu, let's take some questions for a few minutes.
And I guess while we're waiting for some questions to come in, I also wanted to show off a new product that we're actually releasing that can help support us as well. So you might have seen in the past, we've had our mini saber in our previous episode of live design, basically a handheld blowtorch, really cool for a lot of different things. But we're actually currently working on what we're calling the Smith blade. And basically this is a pocket knife, which is actually a multi-tool. So not only is it a full blade, but it has an integrated bit holder on the back. So this I can actually hold 4 screwdriver bits internally in the knife, as well as a bit driver on the back. So you can actually use this as a screwdriver, and it's fully centered. So it's actually very comfortable to use. It's got a bubble level and a piece of tritium that makes it glow in the dark. It has a built-in ruler on the side of it that actually follows through to the blade. So you can actually go all the way across from the back of the knife all the way down the side of the blade. Obviously, it has a file on the back of the knife, as well as we're adding tweezers to this. So we'll have tweezers, a flint and steel in case of emergencies. You're able to light a fire, and a glass breaker on the back. Really, really unique. And the whole thing is actually made of titanium. So the entire knife is super light, titanium body, and an extremely strong high carbon steel for the blade, which will be showing off in a future episode, competing against some of the other products out there. But this will be basically one of the most useful everyday carry items that you'll be able to get your hands on. It even has a pry bar, which is actually, super useful for things like, sheet metal if you need to pop out a rivet or something.
Well, I think I would say a superhero version of a Swiss knife. So
Exactly.
it has much more function than a traditional equipment like this. Yeah.
So Sean actually has a really good question about design tables for configurations. And yeah, in the past we have used design tables for when we're designing the power loader. We had a huge variety of hydraulic cylinders, and different bore sizes, different lengths, different strokes. We're actually able to use the design table to create a single model of the hydraulic cylinder, and then input things like rod diameter, hole size, piston diameter, location of fittings. And then we're basically able just to populate this based on the spec sheet of every one of these cylinders and create a giant array and a full library of every hydraulic cylinder that we have on the power loader, all in one single assembly. And that makes it super, super easy to basically say, like, oh, I need a different size cylinder, get the specifications, import into the design table, and now we have a full model with all the new dimensions. Unfortunately, at the moment, the SolidWorks models are not going to be available, but we are working with Bethesda potentially to hopefully allow us to share more of the designs files with other people, and hopefully even potentially release all the SolidWorks models so that other people can make their own suits. But for the time being, it is just going to be a mesh model that will be available.
Amazing. So, Bogdan, in fact, we have tons of comments in the chat, and I believe this is a really, really happening and learning episode of live design. And I believe we will learn new tips and tricks from you in the coming episodes as well. So with this, I think it's a time to sign off today. And my request to all the audience is, so do subscribe and like this episode, as this is the most functional way to say thank you on YouTube. So we'll be back next month too, and see you then. Have a great day and a great weekend ahead.
Yeah, thank you very much for having me on, and I'm really glad I got to share some of that design experience.